Hello, I'm Jung, student in master's course in Cogno-Mechatronics engineering at Busan National University. The title of my paper is Non-Mechanical FMCW LiDAR with Spectral and Acousto-Optical Scanning. For the first, it's the research background. Recently, coherent detection-based optical range measurement is widely used in various forms from OCT to LiDAR. LiDAR, which is mainly for remote sensing, is drawing a lot of attention these days with the rapid development of automotive and other industrial markets. As can be seen in the table, LiDAR technology can be classified into three major types based on the operation principle. Among these three, the frequency-modulated continuous wave LiDAR is drawing a big attention of its certain advantages. It has high resolution and sensitivity, robustness against interruptions, and velocity obtainability. This video is about the FMCW LiDAR system we have in our lab. As I explained just now, you can see that even in the fog environment, all the existing TOF LiDAR and the human eye cannot distinguish are well imaged. Here is a brief principle of FMCW LiDAR. First, there are a frequency-modulated continuous light and the reflected light. Due to the time difference between two lights, which leads to the slight optical frequency difference, there comes an interference between the two lights. From the interference, we can measure the bit frequency, and by following those formulas, the distance and velocity information can be obtained. However, for the overall development of LiDAR, beam scanning or signal processing as well as measurement method is also very important, and here my research arises. This table summarizes the scanning methods of LiDAR. To apply LiDAR in various moving conditions, solid-state scanners are being preferred and active researches are ongoing. Not only do they have high stability with fast scanning speed, but also have the advantages of flexible beam steering that is difficult with conventional mechanical scanners. However, current technology does not show performance to replace the existing scanners, so a simple solid-state beam scanning technique is required. Therefore, in my study, I've achieved fully non-mechanical FMCW LiDAR combining two different solid-state beam steering techniques. First is acousto-optical scanning using acousto-optic deflector, hereafter AOD. AOD is a device that deflects incident light according to the applied acoustic frequency of electric signal. It enables fast scanning up to few megahertz, and since it is controlled electrically, flexible beam steering is available. Second is spectral scanning based on wavelength tuning and a dispersive element. A broadband wavelength tunable frequency modulated laser was employed, and FMCW ranging and beam steering are simultaneously achievable through frequency modulation and wavelength tuning respectively. Let me introduce our system. The configuration of combined scanner is as follows. Light from the wavelength tunable frequency modulated laser enters AOD and is diffracted in vertical direction. It is diffracted again, this time along for horizontal direction, passing through a transmission grating. As a result, non-mechanical beam steering on 2D is achieved. This figure is about the principle of 3D FMCW measurement with our system. In our system, AO scanning axis and spectral scanning axis are set to fast and slow axis respectively. First, A scan at one point is performed through the frequency modulation of the laser. Then, one B scan is obtained by repeating M times of A scans in the AO scanning axis. These are repeated for N times along spectral scanning axis by tuning the wavelengths of the laser. Finally, a 3D image on N by N pixel size can be acquired. The system configuration is as follows, and this is the specific scanning performance of the combined scanners. It supports 3.5 degrees of vertical field of view, and it supports 11.1 degrees of horizontal field of view. However, AOD causes a small event in FMCW measurement, that is a frequency shift in optical frequency of the light passing through AOD. By the round trip of the light, the optical frequency is shifted twice the amount of the acoustic frequency, and it leads to the shift in bit frequency as well. For moving targets, Doppler shift occurs once more. Therefore, in order to decompose the actual distance and velocity information about the target from the measured bit frequency, a process for compensating the acoustic frequency shift is required, and it can be done by following the equation here. Here is the experimental results. First, a badminton racket is imaged. 3D FMCW image is successfully acquired using our system, and also rocket strings are well distinguished in both axes, proving fine letter resolution. Next, the letters of P and U are imaged. Letters arranged in meter order are well imaged, and a robot arm is also well imaged as shown, and a model airplane is also well imaged as follows. Finally, FMCW measurement with dynamic target is performed. As shown, the distance information is well observed, and at the same time, velocity is also well imaged as can be seen in the point cloud video. To conclude, the non-mechanical FMCW LiDAR system is achieved by combining two different solid-state beam steering techniques. Spectral scanning and acousto-optical scanning are those, and the real distance and velocity information are well decomposed by applying the acoustic frequency shift compensation. Using our system, it was confirmed that 3D images of various static targets are obtained. In the results, excellent lateral resolution of the system is proved, and several meter order of distance measurements are well conducted. Finally, we succeeded in real-time 4D imaging of rotating target in 5 frames per second of frame rate. These are outcomes of my 2 years, and thank you for the attention.